So epsilon nets are one of the very nice and useful applications of compactness for metric spaces, which tell you that metric spaces can be approximated by finite sets to as fine a resolution as you want. So there's lots and lots of applications, more and more in recent kind of metric geometry in active fields of mathematics. So now let's take X to be as, well, let's first, the definition doesn't need anything. So the definition just needs XD a metric space. And a definition, a set S in X is an epsilon net. This is for some epsilon greater than 0. If for all x in X there exists S in S such that the distance between X and S is less than epsilon. So each point, so this is a bunch of points, so that any point is within distance epsilon from some point in the set. So you can see, let me make precise, I was saying you can see. So remark, distance, the Hausdorff distance between S and the whole space is less than epsilon. Okay, or less than or equal to perhaps, because we took the supremum. So this is another way of saying it, that it's a subset of the space. Well, remember Hausdorff distance involves two inclusions. X itself is the neighborhood of X is X itself, but an epsilon neighborhood of X is all of S. Yeah, so this is saying the set of, so I could also write this, well, I don't want to do that because we did it for closed sets, but it's okay. Distance between S comma X is less than or epsilon for all X in X. So bit distance from this set epsilon net. Maybe I'll call it E, so this looks more like an epsilon net. So we have a set E. Okay. So this is, as I said, a finite approximation, and the main theorem here is that if, well, one main theorem, there are a few which are all very useful. If X is, by which I mean X with the metric D, is sequentially compact, then for all epsilon greater than 0, whatever scale we look at, there exists a finite epsilon net E contained in X. So at any scale you want to see, you can approximate by finite sets. So I made general. This actually lets you study limits of spaces using what is called the Grommer-Hausdorff distance, but that's not part of this course. But you can immediately see that we are approximating by finite sets. This will let you also study sequences of functions, many things. Okay, so how do we show this? So let's pick. Okay, so pick sets, if possible. Yeah, or rather, let me put it in a different way. Inductively, pick points x1, x1, x2, xn onwards, such that xn is picked. Distance between xn, xj is greater than or equal to epsilon for all n j less than or equal to n. So inductively pick points, all these points in X, okay, if possible. So let me be more clear. We pick x1, so that is pick x1 if there exists x2 in X such that the distance between x2 and x1 is greater than or equal to epsilon, pick x2, etc. Okay, so now what can happen here? So there are two possibilities. Okay, have so x1, x2, xn, but cannot pick xn plus 1, as for all x in x there exists I less than or equal to n, 1 less than or equal to I, and less than or equal to n, such that distance between x and xi is less than epsilon. Okay, so the opposite of this happens. We cannot find any point which is distance at least epsilon from all of these. Okay, so this means, so one is, this possibility is what we wanted. This means that, where was I? Yeah, so this means that x 1 to xn is a finite epsilon net. We are done. So one possibility, so this happens for some n. So we keep picking points, and at some n this happens. And the other possibility is else we have 2, we can choose such an xi, xn for all n. So what is the consequence? So then we have a sequence xn is a sequence in x, such that for all ij, if I is not equal to j, well, one of them should be bigger than the other, and we chose things such, if I is bigger than j, distance between xi and xj is greater than epsilon. Hence, no subsequence of xn is Cauchy, not even close to Cauchy, because we take this epsilon as the given, greater than or equal to epsilon. Okay, we have a sequence this way, because eventually all points in the subsequence have to be distance less than epsilon, but no pair of points is less than epsilon. Okay, so not convergent. Convergent implies Cauchy is an elementary application of the triangle inequality. I could have directly claimed this is contradicts sequential compactness. So sometimes the term totally bounded is used for this. It's fairly standard, though it's not a great term for this, is having a finite epsilon net. Epsilon net for all epsilon greater than 0. Okay, so remark, so what we have seen is here that sequentially compact metric spaces are complete and they are totally bounded. Okay, so now we can see one more thing from this epsilon net. So while fixed epsilon they are very useful, we can also put together epsilon nets, not just for all, not for all epsilon, but for just those of the form 1 over n. So here is a theorem: if X is sequentially compact, let me spell it out: sequentially compact metric space, then X is separable. It has a countable dense set. Okay, hence second countable. So separability or second countability is automatic for a metric space which is sequentially compact. Proof is just you let En be a 1 over n epsilon net. Then, so each of these En is finite, Okay, so then if I let E is the union n equals 1 to infinity of En, E is a countable, and it's very easy to see dense set. Why is this? Because if I've given a point x and I open set containing it, this contains an open ball of some radius r. Pick 1 over n smaller than that, then E, the epsilon net with n En, where 1 over n is smaller than r, will have a point inside this ball. That is the definition of an epsilon net with a distance less than this. So we see that it has a countable dense set, so it's separable. So the corollary, which is again nice to see here, is that corollary is for a metric space sequential compact. So sequentially compact is actually equivalent to compact. Okay. So Heine-Borel theorem told us for subsets of Rn we had a nice characterization, closed and bounded. But here we have but in general we have epsilon nets, and sequential compactness and compactness are the same. Well, one way, because metric spaces are first countable. The other way, a metric space need not be second countable, but if it's sequentially compact, it's second countable. And we saw sequentially compact and second countable implies compact. So we have a unique notion. The final thing we will see in the next video about these metric spaces for now is that in fact the existence of these epsilon nets implies compactness or sequential compactness, whichever you prefer. They are both equivalent to each other, as we have seen.